Hi everybody, Dr. Pingle here. Today's lesson is going to be on 3D printing. We've actually already taken a short look at this in a previous notebook, but I thought this would be a good chance to dive in a little bit deeper. There are a lot of really interesting both geovisualization applications for this, CAD applications, computer-aided design, and just general sort of interesting uses for this technology. So we're going to dive right in. So a little about 3D printing. This technology has actually come to light really and gotten very popular just over the last few years. Its roots are actually fairly old. 3D printing is often used in industry and by individuals for rapid prototyping and additive manufacturing. So additive meaning that we're sort of adding material to the structure as we go. This is especially useful for prototyping. So, a big breakthrough within the last several decades has been the uptake of CAD, so computer-aided design models, to really prototype out things. But sometimes a physical object is really helpful, and so this lets you create these physical products and work with them and test them out in ways that can sometimes still be difficult to do in a purely computational environment. Most often these things are going to be used, the most common type of printer that you would use is what's called a fused deposit model, or an FDM. What this means is essentially that you sort of lay down one layer of often plastic and then kind of add successive layers to that. The whole process works a lot like a hot glue gun. Essentially, plastic is fed into the machine. It's melted on a print head where the temperature is very finely controlled. And then as that plastic melts, it's deposited onto first a print bed and then each layer. And so it builds the model up layer by layer as you go. So essentially, the way this works is that you create a digital file or you download a digital file. You feed that into what's called slicing software that takes the physical model and chops it up into a series of layers, and then those layers are sort of created step by step by the machine. So in order to clarify how this process works, I thought a time lapse would probably be the easiest. So this comes from a YouTube video linked here below, and what you're seeing here is the successive depositing of each individual layer. Obviously speeded up by a fantastic amount to build a model of the Eiffel Tower. So you can see that we start to reach the point where the arches kind of start to come together. We kind of complete the platform, and then we start building up the next layer from there. So hopefully that gives you some reasonable idea of how this process goes kind of layer by layer. And if you're interested, this is playing at double speed. You can go to the YouTube video, you can watch it at normal speed, which is already speeded up by a great amount, and slow it down if you want to kind of see the particulars, or just stop over at the library and see how these machines do it in person. So the workflow for the generation of these kinds of things goes something like this. A designer might model the object in computer-aided design or CAD software. The two that I use most often are Autodesk 360 Fusion and SketchUp. When we get to the CAD unit in class, we'll talk about both of those pieces of software. But essentially, you sort of use the computer to draw up a very good quality model of the thing that you're modeling. An alternative to that is that you can scan real physical objects. We'll talk about a number of different ways that you can do that. Essentially, LiDAR is one way of scanning the real 3D environment. Photogrammetry is another. And there are some really interesting tools that merge with things like iPads and other devices to do this kind of on the go. And this technology is just getting more and more publicly available. The output from those gets saved as one of a number of different kinds of file types. So we'll talk about two in this class, excuse me, STL and OBJ, which are the two most popular. But there are lots of different kinds of 3D formats. In fact, there are dozens and dozens of these. Some others include DAE, which is a digital asset exchange model, X3D, VRML, which is a virtual reality markup language. So lots and lots and lots of different 3D modeling containers that you can use. That 3D object gets passed into software called a slicer. So we use Kira to do that in my lab, but lots of different slicers are available. That slicer essentially takes that model apart and creates this sort of layer by layer map of how it needs to print it. And that map is translated into what's called G code that directs the print. So sort of lots of different sort of processes this goes through before it's actually turned into a physical printed model. As I said, the mechanism is quite simple. This is essentially just taking something like a hot glue gun, except melted plastic instead of a glue-like glue-like substance, and just sort of depositing this. There are motors that control very finely how this moves on its axis, and it's quite precise. So the level of detail that you can produce with these things is really astounding. The level of detail that you print these things essentially correlates to print time. So the more detailed you want to be, the longer it's going to take to do those. You can produce very thin layers. You can deposit these layers in anything. We'll do anything as small as like a 1/10 of a millimeter. So 10 layers is 1 millimeter, so quite fine. All the way up to about a quarter, or sometimes even like 0.38 millimeters per layer. So each layer is pretty small, and the smaller you make it, the more precise the model looks. One other component of the resolution is the size of the extrusion, essentially. So 3D print filament often comes in a couple of different sizes. We use a 3 millimeter filament, but when it comes out of the print head, it's significantly smaller than that. Something about the size of, say, a millimeter or so. So the level of resolution that you can print is somewhat limited by that. But overall, these things generally produce a much finer model than you can probably imagine. So we talked about sketching these things up in CAD, and I'll show you an example of that here in a second. But this is another example, some relatively recent technology that has come out. There are a few competitors to this, so I've got no particular advocacy for this particular product. But this is one tool called Canvas that essentially consists of a sensor that clips onto an iPad, and then you can use this to gather the data and create the model. So I'm going to play the video now, but the YouTube video is here below. If for some reason this video doesn't render right, feel free to pull the video up on your own.
Canvas is a groundbreaking new application that allows you to capture a scale-accurate 3D model of your home in minutes, all on an iPad. Here's how it works. First, attach a structure sensor to your iPad and launch the Canvas app. Next, start scanning. Canvas captures thousands of measurements per second and combines them into a single 3D model you can use instantly. You don't have to anticipate every measurement or view that you'll need, because with the 3D model, you'll have all of them.
The great thing about Canvas for us is that we can take any of our employees, send them out to a site, have them capture the whole thing, and we have all the information we need without error.
A raw 3D model is powerful, but if you want to make changes using professional tools, you'll need a simplified, editable CAD file. That's why we built a new, first-of-its-kind service right into Canvas. We call it Scan to CAD, and it converts your raw 3D model into CAD within 48 hours.
When I got my first CAD file back, I really wasn't sure what to expect, and when I saw the file, I couldn't believe it. It was so accurate, so thought out, everything was in perfect layers. I can rely on Canvas and Structure Sensor to provide me with more information than my brain would even remember to take a look at.
Clients of all levels want to see 3D modeling. Now that we have Canvas, we can create that same level of project and of presentation for all of our clients. I think it would pay for itself in one project.
To make real-time 3D mapping possible on the iPad, we had to create new hardware and new software. First, we created the structure sensor, giving mobile devices scale-accurate depth sensing. Next, we're introducing a new 120-degree wide vision lens, which means you'll experience our most stable motion tracking yet. And most importantly, we've upgraded our mapping algorithms. We've gone from enabling you to scan objects to now allowing you to capture entire spaces. For the first time, it's actually easy to turn a physical space into data. Space is the new digital asset that you can store and bring with you wherever you go. Canvas is available now at canvas.io and on the App Store, and we can't wait to see what you do with it.
So this is quite a nice piece of software and hardware. Like I said, there are competitors to this, but this does seem to be one that's pretty well thought out. There are, as I said, a lot of different kinds of file formats for 3D printable files or 3D representations of objects anyway. One of these is the STL, so this is probably the most commonly used. Originally an abbreviation of stereolithography, but the technology has really advanced far beyond that. Now we would call this the standard triangle language or the standard tessellation language. And essentially what we're doing, this is not all that much different than a lot of the GIS data that we would work with. It's no different in theory than something like a tin or a triangulated irregular network. It's essentially a series of facets defined by vertices, and a collection of these is sort of an example of that is given above here with the facet normal, which is a direction in space that the face, the facet faces. And then a description, just like any other polygon, of a loop of a series of vertices. There are text and binary versions of this. Obviously text is human readable. You can open that up in a notebook. But most people exchange these in binary. A second very popular format is the Wavefront OBJ file, an object file. It's essentially fundamentally no different than the STL. There are some advantages here. It's a little bit easier to do things like texture the file. The STLs can do that with additional files kind of acting in parallel, but with OBJs it's kind of integrated right from the get-go. These are becoming a little less common as you go, but still fairly popular. And many websites now are available to download different kinds of objects that people have created. I think this is kind of one of the most fun parts of this, is that people are still very much open and sharing about these kinds of models. Very few people are trying to charge for these. So Thingiverse and Yegi and TurboSquid are a couple of examples that I'm familiar with. And there's some others as well. Many of these are free. And I would encourage you, if you haven't already, we've done some of this in early notebooks, but if you haven't had a chance to really play around with some of these, I would suggest that you do that. The drone that I used to fly and still fly sometimes is called the Irist Plus. This is made by an American drone company called 3DR. 3DR isn't making drones anymore, which is kind of sad. But one of the things that they did, and actually one of the reasons why I bought the 3D Iris in the first place, bought the Iris in the first place, is that the all of the parts are 3D printable. So they had released the plans for this even before I purchased my unit, and so if a part breaks, you can just print a new one. And we've done that a few times. I've had a battery bay door broke, a little snap closure broke, and I was able to print a new one and get back rolling with no problem at all. One of the things that I do that's kind of fun is with the 3D printer that I have, if I'm looking for a particular project that I need, a lot of the hardware components don't necessarily need to be metal, and so if there's a part that I could use plastic for that's often sold as metal, I can actually just go and download those 3D models of those objects for free. And print them out at home. So one of the companies that does this is McMaster-Carr, which is a really nice internet vendor of various kinds of hardware. I use this stuff all the time. A lot of times I actually buy the stuff and have it shipped, but occasionally, once in a while, I will print something out. So this is an example of a washer. Basically, you can Google the website, pull it up, and as you look at the parts, you can get an option to save this, in this case, this particular washer, as a 3D SolidWorks object, and I can bring that into some software, export it back out again as an STL, and then just print it on my 3D printer. So if you're interested in a particular project like this, I'm only going to play the first minute or so of this so you can get the idea, but the YouTube link is here below, very easy to find. But this is an example of sort of making some hardware, 3D printing it and turning it into a desk. So I'll play just a minute or so of this.
Hey guys, Vladimir here with Desktop Makes. I've always wanted to make one of those steel pipe desks, but the hardware on that stuff can get pretty expensive, so I thought I would buy just the pipes and 3D print everything else. Alright, let's give it a shot and see if it works. I went to the hardware store, and instead of buying 4 separate pieces of pipe, I bought one long 10-foot one and had them use this really cool machine to cut it and actually thread the pipes for me. I then designed a flange that screws into the pipe, and I use the term design loosely here, and I'll show you in a minute what I mean. I sent this to my CR10 3D printer and printed it with the threads, and the big test here was to see whether it would actually screw into the pipe, and as you can see, it threaded very smooth. Instead of buying additional pipe to use for my back and side braces, I decided to just go with some scrap wood I had lying around. So I cut these down to size and then designed my own custom bracket that would hold the pipe in the wood, which I also sent to the 3D printer. I laid out all my parts, which included the plywood, the pipes, 8 3D printed flanges along with the 3D printed brackets. I marked and pre-drilled the screw holes on the plywood, making sure not to go all the way through. I then screwed the flanges to the plywood, and for some added strength I included washers between the plastic and the screws. Next I attached the legs by threading the steel pipes into the 3D printed flanges, and I'm just really happy at the quality of the threads here on the printed parts. No post-processing involved, I simply popped these out of the printer and got a perfect fit. The printed back and side brackets also attached with a nice friction fit here, but I will be using some CA glue just to help it stay in place. I attached the back wooden brace to the brackets and pre-drilled and screwed these into place. I did the same thing with the side braces, making sure to level it first. These side brackets are pretty much just a miniature version of the back ones. Now came the moment of truth. I had to flip this table over, and to be completely honest, I wasn't confident that this wasn't going to collapse under its own weight. It was a very awkward process, and I'm actually playing this back in double speed so I don't draw it out. The steel legs here are very heavy, but the 3D printed parts did manage to hold it, and I managed to flip it over without destroying everything. That was close. And here is the finished product. I gotta say, I'm happy with the way this turned out. The brackets and the flanges are holding pretty well, and honestly, I did this just sort of as an experiment to see if it could be done. And is it the strongest table I could have built? No, there's definitely some improvements here that could be made, but for what I needed for it, just to sit down, throw my laptop, and create a design, it's exactly what I need. I mentioned earlier that I used the term design a little loosely.
All right, if you want to see how he designed with those brackets, essentially using Autodesk Fusion, be sure to play that video on your own. Again, this is just kind of a fun project, and it highlights sort of some of the creative things that you can do with 3D printing, even outside of geography. Again, I use this kind of stuff all the time to design pieces and parts for the things that I work with, whether it's drone parts, custom drone parts that I'm working with, or other components. It just comes in handy. And as you can see, the level of resolution on this stuff is fine enough that you can print threads. They generally have to be for parts that are of some size, but the tiny threads don't print out so well. But you can always tap those holes, and you can thread those as well if that's what you're interested in. There are a lot of different applications for this, a lot of really exciting stuff. So NASA is experimenting with the 3D printing as a way to supply hard to access areas. The idea would be instead of having to bring things along with you, you could essentially bring a 3D printer and filament for it. And with that, you can make any of the parts that you're going to need to make, whether something breaks or you want to print spare parts or whatever it is. So lots of really interesting applications for this stuff. Archaeologists are using 3D printing as well. Objects are getting scanned. Those scans can be distributed to other people and printed out. They can be used in the classroom. They can be used for study. Lots of really interesting applications for this stuff in that field. Meteorologists are using this kind of technology for some specific purposes. So this is an interesting application where a group of researchers used a 3D handheld scanner on a mobile field unit and basically went out on some of the big hailstorm events and recorded some of these objects. And that gets these things out to people in a way that we just couldn't have done before. So really interesting examples. I actually printed these out myself. Sorry for the background noise here. I printed these out myself, and it worked really well. This used a different approach, so rather deposition. This was a process called SLS, or selective laser sintering. The technology goes something like this: the machine deposits a layer of powder, and then a laser is used to fuse that powder before a next layer of powder is dropped. The advantage to this is that you're basically building a solid block of powder plus object, and so it's adding support to the overhangs as you go. The deposition modeling the computer can actually add supports for various overhangs. So you can build very complicated objects, but removing some of those support structures can be tricky, whereas in this case, the support structures were never fused in the first place. And so essentially a fan or a vacuum sucks all of the excess powder out, and what you're left with is sort of a perfect model without any requirement for attached overhang. This particular stone was about 4 inches, if you're interested. We've seen this in a previous notebook, but Iowa State's Touch Terrain program lets you automatically create prints of terrain. This is a really nice program. It's got several different sources of elevation in it, depending on the resolution of the features that you're trying to model. You could basically draw a box, create some check boxes here for transparency of the hillshade. This is actually just in the viewer. You can select the size of the print. You can select vertical exaggeration. Lots of really great examples of this stuff. It's a really great example of sort of automating what would ordinarily be kind of a tough technology to get into the hands of everyday people, and automating it and creating a web tool that's just very powerful and easy to use. There are lots of other examples of automated tools to create geographically relevant objects. So this is one of them. This is taking OpenStreetMap data and turning it into 3D printed maps. There are a number of different versions of this. So there's Touch Mapper, Tactile Maps, and Blind Web, and basically all of these are oriented to using OSM data, building footprints and sidewalks and things to create 3D printed models for people with visual impairment. It's super easy to use. If you have a relative that could benefit from this, it's just a really, really easy way of making a product to help them out. You can sort of see how easy this is to use. Essentially, just sort of, again, draw a bounding box around what you want and fill in a couple of check boxes, and then you can download the file. If you don't have a 3D printer, you can actually order it directly from that. So lots of really, really great ways to get this out. The whole field of tactile map design is an interesting one. There's a long history of this. This has been around for a couple of decades. People used to use vacuum form printing to make these. They can include Braille as labels, but in a lot of cases they're actually reliant on what can be fairly complex symbolization. So at the bottom image here you can see examples of three different kinds of point labels, or point features, I should say, to represent different things. That symbolization is very interpretable, but it can also be sort of one more thing to learn, a bit of a barrier to use. But tactile maps have been around a long time, and if you're interested in some of these things, please do let me know. This is actually an active area of research for me. One of the ways in which I've been working on this kind of thing is to take indoor and outdoor LiDAR scans and photogrammetric scans to render entire buildings. So not just the exterior spaces, but the interior spaces as well. And the idea is that you can print these out and print them out floor by floor and have a complete rendering of a building. And that can be useful for all kinds of planning. But again, I'm very much geared towards making these things useful for people with visual impairments. The process to do this can be a little bit tricky. So there are a couple of different ways that you can do it. Essentially, what we want to do is go from point clouds to tactile maps. Point clouds can be created through LiDAR, photogrammetry, a number of different things to create them. But essentially, once you have that point cloud, you need to classify it, which is a separate problem, and we'll talk about that in that unit. Essentially, what you want to do is try to create potentially simplified landscape. So you can print these things out directly, and we've done that. So we have full photogrammetrically derived models of campus that include trees, and they're really quite fascinating. And hopefully we'll get a chance to meet in person, and you can see these and handle them yourself. They're really quite a lot of fun. But this all rests on the classification of LiDAR to clean them up and sort of remove noise and potentially remove vegetation that can make the model tactilely more difficult to understand than we might want. LiDAR is particularly useful for maps that are going to be of smaller scales or larger areas. The biggest problem here is that typically airplanes fly at a sufficient altitude that you're not capturing the facades or the sides of buildings. So you get the tops imaged fairly well, but the faces of them are not. And so that can create problems if the 3D structure is complex. And so the way that you usually would process these is you take a point cloud, you'd turn it into a DEM, and you'd create a model from that. And if you're interested in sort of this method of processing, CGIT here at Virginia Tech has done a great job of making both a campus model and some other versions of this available. And feel free to stop by maybe and talk to them about that if you have an interest. Most of my work on these 3D modeling projects comes from photogrammetry. So what I want to do is fly drones, image the area with photographs, build 3D models from those photographs, and then build printed models off of that. When we get to the unit on photogrammetry, you can see how this can be a little bit more difficult. Photogrammetric models tend to be noisier, which makes them harder to classify. And so some of the techniques to do this can be a little bit tricky. But the benefit to this tends to be that you get much more high resolution models. You get a lot more detail, particularly on the sides or facades of buildings. And it's particularly useful for high temporal resolution. LiDAR scans are tough to do. They're not often done more than once a decade right now. And so if you want to get an image of a place that's been under development or a new model, flying a drone with a camera is a lot easier than even flying a drone with a LiDAR. So one of the really interesting applications that I've been working on is basically turning photogrammetric models into tactile maps for people with visual impairments. The next phase of this, the technical work on this is actually already done. We're capable of producing these models. And the next step is user testing. And so over the next year or so, my goal is to try to get these out there to the community and let people try them out and to get some feedback. We will probably start off with some sort of just sort of putting these tools out there and getting some informal feedback, but eventually trying to do some real user testing to try to get some feedback on these specific issues. And as a geovisualization person, think about Tufty and think about extraneous information. What does it take to communicate these models clearly to people with visual impairments? And I think the things you want to focus on specifically are clutter, removing extra features and extra objects, certainly noise from photogrammetric models. But for instance, do you want to include trees or do you not want to include trees? Probably not, right? An unfiltered model is likely to be too confusing. How large of an area do you want? That's going to affect sort of how these models feel. Trying to understand a building that's only a centimeter tall is different than trying to understand it if it's 5 centimeters tall. But if you put these things at scale, if your buildings are supposed to be 5 centimeters tall, then the scale gets really large and you can only look at a smaller area. So there's this trade-off, as always, between extent and resolution and scale, and those things are likely to matter a lot on these tactile maps. We want to make sure that these things have landmarks so that people can orient with them. Just like a satellite photo is not the most natural way to experience an environment, these kinds of maps are not likely to be the most natural way to experience these environments. While I hope that they communicate a sense of place that is often missing from a lot of these kinds of products, there's work to be done to make sure that they're intelligible, and landmarks are an important way of doing that. Labeling is critically important. So on a lot of tactile maps that we've seen so far, there's sort of extensive symbolization, there are legends, there are braille labels that go into these things. And I'll show you here in just a moment some of the things that we're working on with labels. These are a couple of sort of simple examples of this based on a research study that I conducted a couple of years ago. There are products that already exist for people with visual impairments. One is called Pen Friend, which is in the upper right-hand corner. It's a product that includes these little micro dot stickers that you can place on things like a pill bottle. You can use a pen-shaped device to record voice labels, so someone can scan the dot, record, and say this is your blood pressure medicine or something like that. And then when they scan, when they have the pen in their hand and they scan this dot, it'll read back to them what those things are. So it's an alternative to something like Braille for everyday objects that you can't just necessarily put Braille onto easily. And not everyone knows Braille, and so this is very beneficial there. We've been working on a new system for laser-based querying that I'll show you here next. Actually, before we do that, this is an example of applying those Pen Friend stickers to a 3D printed map of the campus at Northern Illinois University, where I used to work. And by putting these labels down on different buildings, we can label things this way. This is a similar example using sort of micro-printed QR codes. So QR codes are another way of communicating information via sort of a dense symbol. We had experimented and printed these things out, and you can use essentially a camera phone to scan these in, and so no special equipment is required. We took that technology one step further to create a laser-based interaction system. Essentially the way this works, and I'll show you a video here. I'll get that going and talk over it. Essentially the way this
QR
works
code
is
read successful. Map Annie Glidden to East Lagoon loaded. The upper left corner is Glidden and Lucinda, North Annie Glidden Road. The bottom right corner is 399 Hickory Street. Parking garage. Founders Memorial Library. Faraday Hall. Altgeld Hall. Altgeld Hall serves primarily as an administrative and meeting space on campus. Graham Hall. Graham Hall contains classrooms, offices, and labs for the College of Education. Davis Hall. Davis Hall is home to the Geology, Geography, and Meteorology departments. There is an observatory on the 7th floor.
So as you saw in that video, essentially the way that this works is you've got a QR code which is on the back of your 3D printed model. The camera reads that QR code. You place the unit on the ground. An automated system using a computer vision package called OpenCV detects the corners and registers everything directly. And then what you do is you use a laser pointer to shine a light on particular places on there that you're querying, and a camera reads those laser returns and sends, essentially uses the georeferencing information that comes in a step that happens with the QR code, and talks to OpenStreetMap and retrieves information about that particular feature. It's a really powerful way of allowing the user community to both add notations via OpenStreetMap and interact with these things in a fairly naturalistic way. We're getting close to wrapping things up. A few other really kind of interesting applications for this. One is color printing is beginning to be possible. So it's already pretty easy to do with what's called a dual head extruder, where you have two different print heads, and essentially it swaps between the two to print out one in color A and one in color B. And in this way you can make multicolored objects. You can also print in two different filament types, which can be particularly handy if you print these, for instance, support structures to support overhangs in one print filament and the main body of the print in another filament. Certain filaments are dissolvable in things like acetone, and so you can chemically wash away the support structures, leaving everything else intact. These, even with sort of dual head extruders or single head extruders that you swap out manually, you can really do some nice things to make the ground features pop out. So in the bottom case here, this is a two filament print with the water printed in blue and the land printed in brown. It's a very effective way of sort of separating out land and water. Another way of doing this is to clip the print surface to a polygon. And in this way, you're not getting these sort of square prints like you get on touchscreen, but the polygons themselves, or the shapes, really kind of come alive in a way that doesn't happen if everything is kind of printed as a single color. Full color 3D printers are also out there. They're very expensive at the moment, but they do produce some pretty stunning visualizations. There are some examples of this online. I provided a link here below. They're just really nice. The way they often work is that the material is inked as it's printed, which is a very clever solution. So instead of having a bunch of different kinds of filament, you sort of have a base filament, and then it's sort of colored with sort of like inkjet printing like technology as you go. If you're really interested in this stuff, there are a couple of really good versions of this out there. So Shapeways is one place that people tend to sell products that are a little bit more finely crafted than the stuff you might find on Thingiverse. This is an example of a full 3D color print of the Big Island in Hawaii. It's a really, really fun way of experiencing this. Essentially, satellite photos are used to color the print structure. And you even have some bathymetry going on here. It's a really gorgeous way of looking at the environment. Similar technology to this is the augmented reality sandbox. I hear tell that geology here at Virginia Tech has one of these. We've built one of these in our lab in the past, so this is a former research assistant of mine demonstrating the 3D sandbox that he had built. This technology was invented by Oliver Kralos at UC Davis, and very generously put out there into the world. We'll look at augmented reality in a little bit more detail when we get to that section. But this was very inspirational because it allowed us to consider the use of augmented reality on 3D printed maps. So the idea is you print on a 3D map, and then you project onto it, and then you can use other kinds of technology to bring interaction to it, like we saw before with the 3D printed maps for people with visual impairments and the laser input. I'll start this image here. This is an example of weather map printed on a 1 meter print of global topography, and it's a way to explore how this overlay works. We used similar technology to create a 3D printed model of Hurricane Irma. And one of the last lectures, we showed you how this can be done and visualized digitally as a 3D model. But we actually created a 3D printed model of Irma as well, using exactly the same approaches. And some of the notebooks for this lecture that accompany this will teach you how to do that. Not everybody has their own 3D printer. They are getting cheaper and cheaper all the time, but there are many places in cities around the world that you can do this in. I'm amazed at how quickly this technology has exploded. We have the benefit of having this stuff here at Virginia Tech, so the library has a bay of 3D printers that you can use in the design studio. Many universities are creating maker spaces, and Blacksburg has its own kind of maker group of tinkerers. They often have these things. So even when you get away from Virginia Tech, I think you can also find opportunities in your community to do this. Libraries in particular, many city libraries have this service now. And you can always order this stuff online. So there are many online mail ordering services where you can upload your STLs and they'll print and ship something to you. So that's not such a bad way to go either. As I said, these things are getting cheaper and cheaper all the time. I looked this up last year, and this is one of the cheaper ones that I saw, $300. I'm sure that these things are around $200 now. The cost of them tends to get bigger quickly as you get larger and larger ones. But for smaller models and small projects, you can find these things really, really cheaply. Most people ask, how much does this stuff cost to print? It's actually relatively inexpensive. You buy filament, you can buy this stuff on Amazon or wherever. This is some of the filament that I use. It tends to be about $20 to $25 per 1 kilogram roll. 1 kilogram roll might last me months, depending on what I'm printing. Individual small prints might be as little as 10 cents to print if you figure in this cost. Big maps that I make that are sort of multi-panel maps, those might cost $20 or $30 to make in filament. But overall, you can get pretty far with this stuff pretty cheaply. A lot of the models that we make, by the way, are not printed sort of in solid form. They're printed with what's called an infill. So the interior structure of these objects tends to be semi-hollow. There's sort of a grid that the slicer puts in as it carves the model up. And it basically builds support structures as it goes. So that the models that you print are rarely solid plastic, although you can choose to do that if you want to. They're usually with a 20% fill or a 30% fill, which is still fairly strong, but saves on a lot of print expenses. So I hope this is a good introduction to 3D printing for you. It's a technology that I'm really excited about. There are a ton of really good geovisualization applications, but a lot of just applications beyond that. So for those of you who have an interest, I hope this is a good start. If you do have questions, feel free to drop by and ask. We have one of these printers in the lab. I have my own personal 3D printer at home, which I use all the time. So it's a great technology, and if you're interested in finding out more about it, please let me know. We've got notebooks on this section. If you're more interested in the technical aspects, you can learn more about that stuff there. And I look forward to hearing from you. Thanks very much. We'll see you next time. Bye.